Hello, everyone. My name is Lequn Chen from Perplexity AI. Today, I'm going to talk about this RDMA point-to-point communication for the large language model systems. And in particular, I will focus on one application that is the weight transfer, but I will also give a brief touch on the KvCache transfer and MoE. So we know that the large language models have been relying heavily on the collective communications because they are great. They are just so great for the structured parallelism. You must have seen this kind of collective operations like or reduce or gather, these kind of operations, and you might have heard of organizations like tensor parallelism, data parallelism, pipeline parallelism. All these things are fantastic use case for the collective communications, and that is why we have been using it dominantly. Until now, very recently, you start to see that there are more and more emerging point-to-point communication patterns. For example, for the disaggregated inference, you want to transfer the KvCache between the prefillers and the decoders. And this is a point-to-point transfer. There's no other peer needs to be involved. Another example would be the reinforcement learning post-training. Here you have the training workers and you have the inference workers, and you need to transfer the latest weight from the training worker to the inference worker. This is also point-to-point. Although it can be collective, but it's better to be done in a point-to-point way. I will show you later. And another important application is the mixture of experts. So MoE models are super powerful these days, but for them, you need to decide which experts to use at runtime. You don't know beforehand, and experts are chosen dynamically. The numbers of tokens sent to each rank is different. You don't know this beforehand. So all this dynamism will increase the difficulty of using collective APIs. Why is collective APIs harder to use for this kind of peer-to-peer communications? The first reason for that is the collectives, they have a fixed membership. So if you have ever used collective APIs, for example, like torch.distributed or NCCL, you know that there is an initialization process, and that initialization process will build a communication world. And for this initialization process, you need to have all the ranks to run this command at the same time. Like it will block here to establish this communication world. Imagine this use case where you have disaggregated inference, where you want to transfer KvCache between the prefillers and decoders, and you deploy this thing to production. And then production traffic can change, right? So you want to respond to this production traffic change. So you want to increase replicas, decrease replicas. But imagine like if you implement this thing with collectives APIs, then you are bound to this fixed sized communication world. It will be very hard to add new members or remove any members. Maybe these members become 40 or something. Anyways, it will be very hard to change the members of a communication group. Besides that, the initialization of the group is also very, very hard, even if this is within an already established global world. So let's say you want to partition this global world into smaller worlds, maybe for point-to-point, or maybe for smaller scale communication. This kind of subgrouping still needs all ranks to participate. So you can imagine that if you want to create pairwise subgroups, then you need n-square communication rounds. This will be very, very inefficient. It will be a huge initialization cost to pay. And the third point, which is also very annoying and hurts performance, that is the collectives that require uniform tensor shape and also the same D-type. So the receiver and the senders, they use the same shape, they use the same D-type. This is usually fine, especially for the structured parallelism. But for example, MoE, you don't know how many tokens will be sent to each peer in advance. So you might have to prepare for the worst case. Then in MoE, the worst case can be 50x or even 100x worse than the average case. Basically, that means you are wasting lots of the main memory wasting lots of the GPU memories and also wasting lots of the RDMA bandwidth. And the fourth reason is that the collective APIs, they guarantee this operation ordering. So for example, let's say we have 1, 2, 3, 4, 4 pages needs to be transferred. The senders send them out sequentially, 1, 2, 3, 4. The receivers must receive them 1, 2, 3, 4, like in sequence. On the other hand, the network is complicated. It can be out of order. That means that in order to deliver this kind of strong ordering guarantees, there must be some buffering or barrier that happens underneath it. So that might reduce your performance. And while these collective APIs, they try to provide this very nice feature of in-order delivery or maybe this operation ordering. On the other hand, the applications, they might not appreciate it, at least for some applications. For example, the KvCache transfer, you have tons of pages that you want to transfer, but I'm fine as long as all of them arrived, right? You don't care about their arriving order. And it's the same for the weight transfer. You want to update all the model weights, but you don't care about the order that they are being updated. So that is the downside of the collective APIs. And if you instead just use RDMA primitives to do this kind of point-to-point communication, things will be much easier. I will give a very brief introduce of this RDMA. So basically, RDMA is a very fast network. The current generation can give you 400 gigabits per second bandwidth, and next generation will be even faster. The most widely used network card for RDMA is the NVIDIA Connect X series, but other cloud providers, they may have their own proprietary network card. For example, we use AWS, and AWS, they have their EFA. Also, other chip makers like AMD, Broadcom, they also have their own network card. The attractiveness of RDMA coming from that it bypasses the Linux kernel. You just don't need any buffering. The user space application can just talk to the network card, and the network card can have direct access to the memory, whether that's a remote memory or that is a local memory, and whether that is on CPU or that is on GPU. Like the network card can just access that memory very easily. Another benefit is that the GPU to the network card traffic, it just stays within the local PCIe switch. So there's no system-wide contention across the system bus. So you can achieve full bandwidth between the network card and the GPU. And RDMA is not a new idea. In fact, it's already been widely used. If you use Nico, across multiple nodes, then it's using RDMA. It's just that Nico and torch.distributed, it wraps up and gives you this collective API abstraction, whereas this point-to-point RDMA primitives. So what are the RDMA primitives? Basically, it's very simple. It has two categories. The first one is two-sided, which means that when you do this send and receive operation, the remote CPO will be wake up. This send and receive is very simple. It's just sending this buffer to the remote, very simple. And the remote will know when this buffer arrives and how long the buffer is. This is very typical. The interesting thing actually coming from this one-sided operation where the remote just doesn't even know that its memory is it's modified. So for this write operation, you can just write. You can ask the network card to just copy your local memory to the remote memory, and remote CPU just doesn't know about it. Very funny, very interesting, and very efficient actually. But what if you just you do want to let the remote know about this write operation? How do you do? There's also this write with immediate this operation that. Besides the write operation, it allows you to attach a 32-bit network, a 32-bit integer to the message, and then the remote will get notified about this 32-bit integer. So you can use this to implement a synchronization scheme to let the remote knows that the transfer has completed. And write and write with immediate, these are the most important thing we use for the RDMA. But there are a few other ones. For example, read. Read is the opposite side of the write. Like you can, instead of writing things to the remote memory, you can also read things from the remote memory. But it will be less performant than write. Also, there are some support of atomic operations, but also they are not as efficient. So how do we use this kind of RDMA primitives for the point-to-point communications? We can use the two-sided operation, the send and receive, use it like RPC. You can use that to send your application control messages, for example, request start, request end, these kind of messages. And then when you need to transfer lots of data, you can use write. And if you need transfer data and also you want to know that it's done, if you want to implement some synchronization schemes, then you can also use the immediate numbers along with the write operation. And if you look at this very simple API, this this send receive and this write, just this very simple primitives. If you build your applications using these primitives, it's actually much easier than building applications with collectives. Because you don't need to formulate a communication world. You don't need to do any subgrouping. You just talk to whoever you want to talk to. And also, it guarantees that there's no any additional buffering. Everything is zero copy from your local GPU to your remote GPU. There's no overhead here. And also, you don't need to worry about tensor. You don't need to worry about their shape, their D-type. You are just sending the buffers. You are just sending these buffers and the length. That's all. So with this background, I'm going to talk a little bit about how to do the model weight update through the RDMA. The use case for this is for the reinforcement learning fine-tuning, where you need to use inference engine to generate samples for the training workers to train on. And then these inference engines, they can have dedicated GPUs. And after each training step, you want to send the latest weight from the training workers to the inference workers so that the weight keep in sync. If we look at the history, previously the weight transfer time can take 10 to 100 seconds depending on how big the model is, which greatly slow down the training speed. And now with our RDMA point-to-point transfer scheme, you can just transfer very, very big model in 1.3 seconds, very fast. And this is including some GPU operations like quantization, this kind of computations. So I would say it's very fast. It makes the RL training much faster. How do we do that? Since this is Ray Summit, I have to say we do use Ray for IO training. It's very easy to use. Previously I didn't know about Ray, and then I just look at this document. I saw this Ray.remote, and then that's all. That's all I need to know. And boom, you have your IO training loop orchestrated by Ray. You can see that we have three components here. We have the training workers, we have the rollout workers, and we have a controller node. And the way that we do weight update is very simple. It's as simple as putting an elephant into the fridge, except that it needs 4 steps instead of 3 steps. The first step is collecting the metadata. So we want to collect from both the training workers and the inference workers about all their parameter metadata, like their name, their shape, and how they are partitioned across the nodes. And then next step, you can compute a weight update schedule. This is just some name matching and some very simple greedy algorithm, and then you can compute a weight transfer schedule. And then you send this schedule to all the training workers. Note that you don't need to send it to the inference workers because we don't actually need the involvement of the inference workers. All these three steps, they happen at the initialization step. And then what happens in the training loop is actually very simple. In the training loop, you just tell the training workers to start the execution of the weight transfer. It's very simple. You don't even need to tell the inference worker to do anything. And how do we actually execute this weight transfer? We actually formulate it as a pipeline. So on the training worker side, because of the GPU memory usage limitation, right? We want to sometimes offload the model weights onto the CPU memory, right? So when you start doing the weight transfer, the first thing you might want to do is to bring the model weight back from the CPU memory to the GPU memory. And then after that, because we shard our model parameters using the PyTorch FSDP, which means that a tensor, a parameter will be shared across multiple GPUs and potentially across multiple nodes. So we need to first call the full tensor method to collect the full tensor of this parameter. And by the way, this full tensor operation, it is actually an all-gather operation. It is a collective communication operation. So after this full tensor operations, and we can do some processing for these parameters. For example, you can do some projection fusions so that it matches the format on the inference engine. And then you can do FPA quantizations. For example, if you do training on the 16-bit and you are doing the inference on the 8-bit, then you want to do a quantization here. And once you have done with the GPU operations, you can just send this tensor out through the RDMA to whichever inference GPUs. And you can see it is utilizing different types of hardware resources. That's why we formulate it as a pipeline. And then you can save lots of time by overlapping. And the result shows that it's very fast, and our implementation is very simple. But why is it fast? Why is it simple? One big reason for that is if you look at the traditional way of updating the weights, it's basically a rank 0 based approach where on the training node side, you want to gather all the tensor data to the rank 0. And then you send out the model weights from rank 0 to all the inference node. And very apparently, this network card associated with rank 0 will be the bottleneck. So you are only utilizing one network card. Whereas if you do a point-to-point transfer, then you are utilizing this point-to-point communication. You are utilizing the full cluster bandwidth. That is why you get much higher bandwidth. Another reason is that we are using this kind of one-sided data transfer. We don't need coordination from the inference engine. There's no change to the inference engine. You don't need to have RPC method to tell the inference engine that, okay, the weight has been updated. So there's no overhead of extra buffer, and also there's no overhead of RPCs. And then there are a few other reasons like the pipelining and the static schedule that we have covered. And also when we are engineering this thing, we try to break it down into individual components so that you can have unit tests, and also like you can optimize them individually. So that is mostly everything about the weight transfer. But let me also briefly talk about the KvCache transfer for the disaggregated inference. For this, because we are using point-to-point, we are no longer bound by this world. There's no world. So if you have a new prefiller replica that you want to add, okay, just add it. You can just immediately talk to anyone. Also, we have some other techniques to support layer-by-layer transfer so that you can overlap the computation time and the network transfer time. Also, our solution supports CUDA graph, so you can also use CUDA graph in your prefill. The high-level solution basically agrees with what I previously said. We use two-sided send and receive for this RPC-like control message exchange. We have these three types of message. One is start prefill, basically just tells the prefiller about the input IDs, the KvCache page indices, and then the remote memory region information. And on the failure side, like we have some cancellation message that can happen. Interesting thing is that we don't have a finish prefill. Like we have a start prefill, but we don't have a finish prefill message. That is because we use one-sided write with immediate RDMA op to send the KvCache page, and we can just count how many 32-bit integers, how many immediate numbers that we have received. Then we know that, okay, when this KvCache transfer is done. So there's no need for a separate finish prefill message. That is the gist of it. I'm not going to talk about too much detail about it. Then next topic is the MoE. So MoE are powerful, and for MoE you need to use a communication library to let it scale across multiple nodes. Typically people will use DeepEP. DeepEP is super great, it's super smart, and also super fast, but you cannot use it everywhere. So DeepEP, it uses IBGDA, which is a very fancy technology that is only available on the NVIDIA's network card. And also it directly uses the ConnectX driver, so you actually cannot port it to other network card. Why is this IBGDA very important for the DeepEP? Why is it about? So traditionally speaking, we know that the RDMA network card can read data from GPU directly. There's no need to go through CPU, right? But the action of initiating a communication, this very action of initiating communication has to happen on CPU. So you can imagine now you are running this MoE model, you are running a GPU kernel, and this GPU kernel wants to send out message to through the RDMA. But because GPU cannot talk to RDMA network directly, so it needs to ask CPU for help. That is why on the left-hand side, you see this host proxy approach that has lots of detour. Basically, like GPU tells the CPU that, hey, can you do me a favor, send this message out? And then the CPU tells the network, and then network read the data from GPU. And then once it finishes, the CPU tells the GPU that, okay, it's done. So it's a very long detour. Whereas on the NVIDIA platform, the ConnectX network card, it supports this IBGDA technology, which allows the GPU to directly talk to the network card, very conveniently because they have control over the GPU and the network card. So with this thing, you can cut latency, and also you don't need this CPU involvement. But other platforms like AWS, they don't have this technology, but we still want to run things on other cloud providers, right? So we just think about this problem. Like we think about, okay, we are going to accept this reality that we don't have IBGDA, so we are going to always have CPU as a middleman to facilitate this communication. But how bad can that be? So we do a measurement about this CPU to GPU PCIe latency. It turns out that it's only 2 microseconds. If you think about the execution of MoE kernel, usually that would be maybe 100 or even 200, even longer microseconds. So adding 2 microseconds or even 10 microsecond latency overhead, that's pretty much acceptable. That is the insights that we have for this thing. So we just dive into the implementation using the RDMA primitives. That one will have even more technical details, so I'm not going to talk about it here. But here I'm going to share the performance results from our MoE kernels. This is the decode setup, so we have 128 tokens per rank, and this is assuming the DeepSeek V3 architecture. Here, you can see we're comparing our latest kernel with DeepEP, and also with our previous NVSHM-based kernel. You can see on the CX7, which is the NVIDIA's network card, we are even faster than DeepEP, even though we are not using the fancy IBGDA implementation. And on EFA, we are also achieving very reasonable latency. And the reason why it is slower than CX7 is just because EFA is slower than CX7. And also we are working with AWS to try to make things even faster. And another interesting thing is comparing our old kernel and our new kernel. So our old kernel is based on the NVS HPM, and it provided the access to the IBGDA technology. So if we run both kernels on the CX7, and with our new kernels doesn't run with IBGDA, but the old kernel runs with IBGDA. You can see that it's still faster than our old kernel. That means that perhaps this is not the most important thing to have. Like your implementation matters, your system design for this kernel matters. So by improving the implementation and by improving the system design for the kernel, we're actually able to beat the IBGDA-based solutions. So this is the code performance. We are very happy about it. For the prefill performance, it's slower than DPP, we have to say. Because DPP, they are just so smart. They have some very fantastic optimizations. They transfer less bytes than us through the RDMA. So that is why they are faster. We haven't implemented this optimization yet, but if we implement that, I think we can catch up. But anyways, this is still very usable. Like you can still use this thing on EFA. I think our kernel is the only kernel that runs on AWS. So we can enable big MoE models on the AWS machines. What does that mean? So here is two examples of running two very big models end-to-end. And this is the cost and the latency trade-off. And let's look at the left-hand side. This is the DeepEP v3 model. You can see three lines. That is with 32 GPUs, 16 GPUs, and 8 GPUs. And 8 GPU is just a single node. And you can see that if you can use more GPUs, then your latency and cost trade-off becomes even better. So you can get lower latency and lower cost at the same time with more GPUs. That is why this multi-node communication MoE kernel is very important. And on the right-hand side, you see the Kimi K2. This is an even bigger model. This is a 1 trillion parameter model. You can see that it misses the EP8 curve. And that is just because this model is too big to run on a single node. So our kernel enables you to run this kind of trillion parameter model on cloud providers like AWS. Yeah, to summarize what I have talked about, the collectives are great. They are great for structured parallelism, but there are some emergent point-to-point communication patterns that are slightly awkward on the collective communication side. So we can just build these applications on top of the raw RDMA primitives. And these RDMA primitives, they are very simple, just send, receive, write, very simple. And they're very efficient. And we have 3 use cases for that, one for the weight transfer, one for the KvCache transfer, and another for the MoE. We just published this research paper. We just put it on archive. So it has all the details in it. If you are interested in it, please read it. And also we have our code open sourced, so you can try all these things on your own. It's on GitHub. That is all. Thank you, everyone.
We got time for a couple of questions.
Thanks, Lequn. This was a great presentation. One question was about the Kimi's checkpoint engine that they use for weight update. So do you have any, do they use a similar technology of RDMA, or is it a something different implementation? For
It's RDMA.
It's also RDMA.
I know that in the Kimi checkpointing, they use also a technology called CUDA IPC. How does that compare with RDMA?
Yeah, CUDA IPC works within a single node.
I see. And how is that different from like just using nickel, for example?
You mean for the weight transfer?
Yeah.
For nickel, it will be a bit harder to do point-to-point. You need to write your code in a weirder way. But I haven't tried benchmarking it. I don't know about the performance difference.
Okay, we'll take the last one, and then you can catch him right in corridor and ask more questions.
Hi, thanks for the nice talk. How do you handle failures?
Failures of
If NIC fails or a GPU is unreachable during transfers or updates?
These are more on the application side. So our RDMA library can give you this error results, right? So if the network is disconnected for any reasons, this transfer just fails, and then the applications can handle it. For example, we do have lots of error handling logic in our disaggregated inference, and also like you see that we have some cancellation message, right? These are the additional application message that you need to implement a very robust system.
Thank you.
Thank you, Lequn.